Alrighty, for those of you that are on, go ahead and open up electric, please. So what we're going to do today, because I have a faculty meeting at 9:15, is we're going to set up electric to be able to process the analog circuits that we're going to be building in this class, and then also going to try to configure it to work with LT Spice so that we can do some simulations. And then we're going to build the current mirrors that we designed in class on Tuesday. So the first thing that you're going to need to do, hopefully you guys can all see my mouse, is click on this little icon at the top that looks like a wrench and a screwdriver. I know you can't see the window that pops up on my screen, but it should bring up a menu that is called Preferences, and the first thing that it brings up is called General User Preferences. And I don't think we're going to be dealing with any circuits that are too terribly large here, but we're going to go ahead and increase our maximum memory from the default, which is I think 64 megabytes, to 512. And let's go ahead and make the maximum permanent space 512 as well. So click the apply button after you make those changes, and then let me know if you guys are able to follow along.
Can you repeat that last part?
Sure. So we are increasing our memory. So if you go into the general settings, so under categories, there's a folder called general, and then under that folder general, there is also a little bullet icon that says general. Towards the bottom right-hand side of that menu, there is a memory section, and it has a little window for maximum memory and a little window for maximum permanent space. Set both of those to 512.
Okay, thank you.
Yep. Anybody else? Are we all caught up to that point?
Mm-hmm.
All righty. Now go to Tools. So the Tools folder, and at the very bottom, the last bullet point is called Weld Check. Click on that. And it should pull up a little window that says Weld Check User Preferences, and there are two columns, one for PWell and one for NWell. And there is a little circle box that says must have contact in every area, must have at least one contact, and then do not check for contacts. For the PWell and the NWell, make sure that it's checked for must have contact in every area. Then below that, there is a square checkbox for PWell that says must connect to ground. Make sure that is checked. And for NWell, there is a box that says must connect to power, and make sure that's unchecked. And the reason why we are unchecking that box is because we couldn't have an NWell resistor in our analog designs if that box were checked, because it would always force all bits of NWell to be connected to our power supply voltage of 5 volts, which means we'd never have a voltage drop over our resistor. So when we're building an analog circuit, we need that box unchecked. let me know when you guys finish up with that.
I'm good.
All righty. Now click on the technology folder and click on scale. And you'll see a big list of different things. We are going to be using MOS, M-O-C-M-O-S, with a scale of 300 nanometers. So at the bottom of the left-hand side of the little window, you can change the technology scale from its default value. I don't remember what it is off the top of my head, but it needs to be now 300 nanometers for a MOS technology. Let me know when you're done with that. All righty. And go to the technology bullet point under technology. And that brings up the technology project preferences window. Make sure that P substrate process in layout technology is checked. It should be checked by default. For our MOS technology, we have 3 metal layers. The sub-micron rules circular checkbox needs to be checked. The box that says second polysilicon layer needs to be checked. And the box that says analog needs to be checked. Let me know if you have any questions or comments about all of that.
Sorry, my audio cut out. Can you just tell me which file that's in?
So if you go to technology, the subfolder technology, and then the bullet point that says technology. I really wish Zoom would show these submenus, but I don't know why it doesn't.
And you said analog needs to be checked and...
Analog needs to be checked. Second polysilicon layer needs to be checked. Sub-micron rules needs to be checked. And the number of metal layers needs to be set to 3.
Okay, thank you.
So that should have everything set up for creating analog components and all that kind of stuff using electric. So if that analog box weren't checked, we wouldn't have predefined high-res poly 2 resistors or poly to poly 2 capacitors and things like that. We would have to build all of those manually. By checking that analog box, we have access to all of those things, and it'll save us a lot of time. So now here comes a little something. Why is this menu being weird and being way up there? So if you click on the tools folder and go to spice.cdl, or spice/cdl, the bullet point, this is how we configure LT Spice to work with our to work with electric. I'm trying. My menu's placed partially above the top of my screen to where I can't see everything. Okay, so we need the Spice engine set to spice 3, and the spice level set to 3. Set the resistor shorting to none. Parasitics set to conservative RC. Globals set to use dot global block. And the spice primitive set to spice parts. For the checkboxes on the right-hand side of that first area, right VDD/ground and top cell should be checked. Right dot end statement should be checked. And right MB subcircuits should be checked.
Can you repeat which ones need to be checked?
I'm sorry, I couldn't hear whoever was saying something.
Can you repeat which boxes should be checked?
Sure. Right VDD/GND, right dot end statement, and right empty subcircuits.
Thank you.
All right, so now in the bottom area where it says running spice, we want to make sure that after writing deck, we run and ignore the output. And so here's where things are going to be a little bit different for pretty much everybody. So I'm going to put some stuff in the chat if I can, which means I have to find the chat on this other computer. So where it says run program, this is entirely dependent on where you installed LT Spice. So I'm putting where I installed it, and it actually is important that you use the quotation marks here. So it's either going to be, if you did a normal install, it's either going to be in program files or it will be in program files x86. Everything else should be the same. So take a moment and try to figure out where you installed LT Spice to your computer. And that's the information that you'll put in the run program box. Let me know once you've all figured that out. Anybody having trouble finding out where they put their LT Spice file?
No, I'm good.
All right. Everybody else have their LT Spice file located and the correct file path put in the run program box.
Yes.
All right. So the next thing we're going to do is fill out the with args box, and that's configuring LT Spice to handle it. And so this is a weird string, so I'm just going to put it straight into the chat and put it all in, just literally copy and paste it. It should be one single line. It's just my chat window. Isn't Lord? Yeah. So that -I $, file name, blah, 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 all that kind of stuff needs to be put in the with args box. Let me know when you've got that done.
I'm good.
All righty. So now you just need to make sure that the box that says overwrite existing output file, no prompts is checked, and the box that says run probe is checked. Also, that the thing under run program where it says use directory, that's just where you can specify all the temporary spice decks, like where all your spice decks and stuff like that are going to be saved. I don't think it particularly matters where you do that, but if you don't do it, I think it puts them all on your desktop. So don't be surprised if you get a whole bunch of weird files up there. But you can specify a directory. So for me, I just put it as a C:/electric where I'm storing all of these files. So after you have those boxes checked for override existing output file and run project, click the apply button and then click OK. And now we're actually ready, hopefully, to start using electric. So what I've done is I've clicked the Explorer button here, and I'm just going to rename this blank library, and I'm going to call it ELEN 438_211 because this is the first quarter of the 21 academic year, and that's the way tech labels stuff. So once I've got my library created, I can right click on the library and create a new cell. And I'm going to call this guy basic_current_mirror_v1. And I'm going to save this as this cell will be a layout cell. So let me know when you all have your layout cell created.
Ready?
All right. So what we did on Tuesday was we did the math to figure out effectively what size resistor we would need to bias a simple NMOS current mirror. So now we are going to make that NMOS current mirror and see if it behaves as we expect. So if you click on the Components tab, at the bottom right-hand side, there is NMOS transistor. Left click on that, and then left click somewhere in your field to place your transistor onto your substrate effectively. Once you have your transistor placed, hit Control I, and that will bring up a menu. It's called the Node Properties. I'm not really sure why Electric considers all components as nodes and all wires as arcs. So that's just a little bit of just the way Electric classifies stuff. Our math was based on a 10 width, 2 length transistor. So change the width field to 10. And then click Apply and OK. Once you're done with that, you should see that your transistor has grown significantly in size. The next thing that we're going to do is click the Tools menu, come down here to Simulation, and Simulation Spice, and click the Set Spice Model button. Actually, we need to do that with the transistor selected. So left click on your transistor, then go to Set Spice Model. And the reason we have to do this is because if we don't, our simulation won't know what parameters to use to model the transistor. So right now, you can see hopefully that there's, let me zoom in actually. So I have my transistor selected, but what I actually want to select is that text. So I am going to Control left click until the X over the text becomes white. Whatever is white is what's selected. Then I'm going to press Control I, and it'll bring me up a big box that says Text Properties. And I just want to change where it says Spice Model to NMOS, N-M-O-S, and click, actually I want the text size to be 1.5, so it's a little larger, and click Apply, and then OK. Let me know when you're caught up to me at this point.
I'm there.
Mitchell, you cut out a little bit, so I'm not sure what you were saying.
I'm there.
Okay, cool deal. So I'm going to zoom out. So we have our transistor. The pink is the polysilicon layer. The green is the active layer. And so we have this guy well set up, but we don't have any connections or anything to it right now. So we need to put in an active region. I'm going to put one below and one above. I've left clicked on the one below. I'm pressing Control I to bring up that properties menu, and I'm changing its X size to 10. So I made it bigger, and I'm going to do the exact same thing the one above. So I left click on it to select it, press Control I to open up the properties window, and then change the X size to 10. Now I'm just moving it around a little bit. You can see that it was telling me that there was an error a moment ago. That's because I don't have the active regions connected together. So if I left click on this bottommost and active node, and then I right click on my NMOS transistor, it creates a wire of N plus implant connecting my transistor to this active node. I can then left click on the active node and move the active up to where it says the inactive spacing is 3. If I move it beyond that, it will tell me that I get an error. So with it at 3, if we press the F5 button on our keyboard, we should see now that we have 0 errors and 0 warnings. If we move it up half of a grid unit, it actually still tells us 0 errors and 0 warnings. So I'm not really sure why it's letting us get away with that. But let's back it off and set it at 3 just because that's what the design rules say is supposed to be the spacing. And we're going to do the exact same thing for our top active region. So we left click the active region to select it, right click it to create a wire that connects the two active regions, and then drag it down.
I have a question.
Yes.
I can only move mine in segments of 1, and it just happens to be on the half. So as close as I can get is 3.5, and then it goes to 2.5. Is there a way to bypass that?
So let's see. I'm trying to remember. Yeah, okay. So what I just did was I clicked on, and I don't know why these menus are up here. On my second monitor, it's showing the menu where the top part of it is no longer on the screen. But I clicked on this little guy up here where it says 0.5. This is the grid user preferences. And down at the bottom right-hand side, it says alignment of cursor to grid. I have mine set to size 5, the smallest, and so that's 0.5 in the horizontal and 0.5 in the vertical. So it sounds like yours, these are set to size 4 to where you can only do ones, or yeah. So change your preference for your alignment of cursor to be 0.5 to 0.5 for the horizontal and vertical, and that should fix that, I believe.
That did it. Thanks.
All righty. Okay, so I'll let anybody else who was having that issue catch up for a moment. The next thing that I'm going to do is place a metal 1 to polysilicon 1 contact. So that's the black square surrounded by a purple square surrounded by a pink square where my mouse cursor is. I'm just going to go drop that next to the edge of my select region there. Actually, that's not select, that's the P weld this guy's sitting in, but anyway. And we're going to connect to that momentarily. But for now, once everybody has that guy put in place, what I'm going to do is I'm just going to drag my cursor and make a box around my NMOS transistor. I'm going to shift left click on that contact to deselect it. And then I'm just going to press Control C to copy it. And then Control V will let me place another one. It's going to be identical copy because we have 2 identical NMOS transistors, and I'm lazy and I don't want to spend the time building the whole thing again. And I'm just going to butt it up right next to the other side of that contact and make sure everything is aligned like so. So I should have 2 NMOS transistors, and in between them is a polysilicon to metal 1 connection. So let me know when you guys are, your screen looks similar enough to mine.
I'm good.
All righty, so in our current mirror, for our basic resistor bias current mirror, the gates of our 2 transistors are tied together. So I've left clicked on the polysilicon area of my left NMOS transistor. And now I'm going to right click on that contact, and that creates a polysilicon wire connecting that node. And I'm then going to also right click onto the right NMOS transistor, and I've tied the two gates together. And just to make sure we haven't introduced anything funny in here, I'm going to press F5, and I can see that I still have 0 errors and 0 warnings. Now what I'm going to do is I've left-clicked the top active region, and I believe if I right-click, this is going to give me green. Yeah, so that's not what I want. So I'm going to press Control-Z to get rid of that. And give me the metal. Still that. All right. I'm going to left click over here on the blue line because this is metal 1. That should make it easier. There we go. Yeah. So then when I select the top active region, it's letting me grab the metal layer. And I'm just going to, so I right clicked out here into space to give me a bit of wire, and I'm grabbing that pin, which is that little dot in the middle, and just moving it to the right, and that's extending my wire. And I'm going to then right click on my contact, and what this has done is it has tied the drain of my transistor M1 to the gate of transistors M1 and M2, because in my basic current here, the drain of my M1 transistor is connected to the two gates. One thing that we haven't yet done is establish our body connection. So we're going to need a P-well contact. And it may be kind of hard to see, so I'm going to zoom in. I'm going to make this P-well contact have a X size of 10 as well. And I'm going to move it up until the yellow area, which is the select, is just butting up against the yellow area of my NMOS transistor. I'm going to press F5 to make sure I don't have any overlap. So the Mosfet rules for the distance between selects is 0. So I can have them literally right up against each other and be okay. But if they overlap at all, like if I move this up half a unit, I get errors. And those errors are just telling me that I need to move this guy away. And I'm going to copy this guy and put another one for my other transistor. And I'm just trying to scooch it up. Let's press F5. So this body connection is what's going to be tied to ground. The whole purpose of this body connection is to make the substrate in the area of these NMOS transistors have no potential. So I have created a metal arc between the two, and just to be clear, what I did is I left clicked on the left one and then right clicked on the right one, and that gave me a metal wire because my metal is still selected on the left hand side there. And I'm just choosing a point here in the middle, and I'm making a little stub, and that stub isn't going to do anything except give me a pin here. And what I'm going to do with this pin, so make sure that you have it should look like a box with a dot in the middle of it selected, and then press Control-E. that's going to pull up a window that says export name. And we are just going to type in lowercase g and d here. So all that's doing is saying that this is where our electrical ground connection should be. If I didn't have that, so let me delete that export real quick. If I run a well check right now, so let's see, that will be under ERC check wells. I get a well check error, and it's because I get two of them. And it's because I have two regions of P well that aren't tied to ground, and I've explicitly stated in my setup that I need to make sure that anytime I have P well, it's tied to ground. If I do that export in, and I run that well check, I don't get any errors anymore because I've let the program know that these two P wells will be tied to ground. To avoid body effects, I'm going to tie the source of each transistor to the body. So if the source and the body are at the same potential, then we won't have any body effects. So I've left clicked on the active region for the bottom active region for the left NMOS transistor. And now I'm right clicking here and I get this big wire and it actually extends beyond the P-well connection. And so I can fix that by making sure that I have the wire itself connected. So the node, so it looks like the box around blue metal 1 region. Press Control I, and at the very bottom left, there's a button that says More. Click on that. And then you should see things that say rigid, fixed angle, slidable, etc. Over where it says end extension, it starts as tail only, and that's the default setting. Change it to neither end, and this will make our metal not extend past where we want it to. Press apply and press OK. And now we effectively have a big fat metal wire connecting the source of our left NMOS transistor to the body connection. And we'll do the exact same thing for our right NMOS transistor. Ooh, that's a very odd place. So I'm just going to slide it over like so. Control I, make my extension be neither end. Click apply and OK. And just to make sure everything is hunky-dory, I press F5 and see that I don't have any errors. So let me know when you guys are caught up to this point.
Good.
All righty. So I'm going to zoom out a smidge here. So I have my transistor M1 and my transistor 2 properly configured. So now I need to put in the resistor. And because I'm running a little bit short on time here, we're going to fudge this slightly. So if we go over to the bottom left-hand corner, we can choose a bunch of different components. We want to make sure that high-res poly 2 resistor is what's chosen. And I'm just going to drop this guy up here towards the top. And I'm trying to line up my contacts here. So let's see if it gives us an error because the high-res layer is overlapping the P well. It does not, so that's fine. Okay. I'm going to left click on the metal region of my top active layer, right click here, and I've made a wire. And just to make it similar to everything else, I'm going to change the size of this wire. So right now it has a width of 3, and I'm just going to make it a width of 4 so that that's just a personal preference for me, so that it's just it doesn't look like stub. So the width of the metal region around the contacts is 4, so I just try to make most of my metal runs to be 4. And click OK. if I left click on my resistor and press Control I can change the ratio of the width. If the width is anything less than 10, I'll get an error. My length right now is 40, which means this is really just 4 squares. So with these resistors, electric and by extension LT Spice can't really tell what the resistor value is because that's not part of the model file for whatever reason, the resistance. So instead, we go down to where it says high res poly 2 resist ... and we literally just put in the resistance. So for this guy with high res poly 2 being what is it, 1,000 ohms per square effectively or something like that. This would really be a 4 kilo ohm resistor, but because I don't want to spend a lot of time making a folded 200K, I'm just going to tell the computer to treat this as a 200K resistor, even though it's not physically sized correctly for now.
Where did you say you typed that in?
So if I have the resistor selected, press Control I, underneath all of the physical dimensions, and you might have to have clicked the More button as well, but there should be a little box where you can type that says high res poly 2 resistance, and I typed in 200K.
Okay, I'm good.
All right. So I hit apply and I hit OK. Now I'm going to click this right metal area for my on my resistor, and I'm just going to right click up here to make a wire extending out to effectively nowhere, and I'm going to export this pin Control E as VDD. So that's where my power supply voltage is going to go. And so technically speaking here, our current error is complete. The only problem that we have is that we don't have a load connected to the output. And so I'm going to fudge that so we don't get into a whole bunch of trouble here. So I'm just creating a little metal wire, and I'm going to export and call this VDS2 so that we can control the drain source voltage and see how this guy behaves. I'm going to run a design rule check, hitting F5, everything comes back okay. So now I'm going to put in some spice code. So if I click miscellaneous and come down here to spice code, this is where I can write in actual parameters for what I want LT Spice to do. So with that text selected, because it has the white X over it, if I press Control I, it brings up a text code or text properties window for spice code. I need to select the multi-line text box at the top right, and then I'm going to type in the following lines of code. VDD space VDD. So this is how we are defining our power supply voltage. 0 DC 5, enter. Then I'm going to do VDS2 0 DC 0. I'm not entirely sure if this second line is needed. I'm effectively just initializing this voltage. Then I am going to type dot DC. So this is telling LT Spice to do a DC operating point sweep, where I'm going to change the value of VDS2. So I'm going to start, let's see, VDS2, start from 0 and at 5 volts in 1 millivolt increments. So that's dot DC VDS2 space 0, space 5, space 1M. And you'll see all those show up on my screen in just a second. And lastly, I'm going to do dot include C:/electric/C5 models.txt. So let me change this to 2. So you guys should see my spice code show up on my screen now. And so that dot includes C:/electric/C5 models.txt. That's where I saved those C5 models that I gave you guys in the resources section. So whatever file path you have, that's where that needs to go. But we're running a little bit short on time, so I'm gonna kind of charter through here for a moment. So if we go to tools and we go to simulation spice, the topmost option says write spice deck. And so what that's going to do is it writes a spice deck for the network that we've created. So let me switch over to LT Spice real quick. So there is no schematic associated with this. It's literally just a network telling it how the different things are connected. We can see with the model files loaded, it tells us the area capacitance of all these different things, the resistance of the metals, et cetera, et cetera. I don't know why it's got all the way up to metal 6, but yeah. And then down here, it's telling how everything is connected within our device, then tells us our extracted parasitic and things like that. It doesn't really tell us where they are, it just tells us all that information. And then finally at the very bottom, it actually runs our spice code. That's particularly important for us right now. It pulls up a blank graph, and that's because we haven't told it what traces we want to put on. So what we're going to look at, if I click at traces, we're going to look at the current through the resistor. So that is represented by this I open parentheses RP2. So that's resistor poly 2. It's the only one, so that's the one we're going to look at. And we're getting a current of 19.87 microamps. So pretty darn close to the 20 microamps that we were expecting based on our analysis that we did on Tuesday. And we can see if we add another trace, so we're going to look at the drain current. So it'll be ID of MNMOS1. So that's the drain current of our right resistor. For some reason, it's showing up as negative. Not entirely sure why. So I'm going to right click it and just put a negative sign in front of it. And we can see that when we're getting approximately 20 microamps when VDS1 is exactly equal to, or pretty close to 1 volt. And above that, it's getting larger and larger and larger. That's because of channel length modulation. We could go back to our our electric file and export VDS1. Literally just put a pin on there to say we want to look at this particular voltage, and we would see that when VDS2 is equal to VDS1, we're right at the 20 microamps or within, you know, a couple of nanoamps of it. So our current mirror is behaving very, very well right now. So, like I said, you guys may not have been able to follow along with the simulation just because you may not have put that model file exactly the same place that I did. If you did, you should get pretty much exactly what I'm getting. If you didn't, the dot includes C:/electric/C5 models text. Just make that go to your right file path. So let's go back over to electric. And I'm going to create a new cell, and I'm going to call it basic current mirror V2. Okay. And now we're going to work on, if we have time, we have 20 minutes maybe, our Mosfet only current mirror. So I'm going to start with an NMOS transistor again. And this time I'm going to do something slightly different. I'm going to rotate it by pressing Control J. Press Control I to open up its parameters. It needs to be 10 by 2. Hit apply. I'm going to set the spice model again. Control left click until the text is selected. Press Control I. Change this to NMOS. Actually, I need to rotate that text as well. So I'm going to go to the rotation field and change it to 90 degrees. And I'm going to make the text a little larger, so I'm going to change the text size to 1.5. I'm going to put an active region over here on the left-hand side. Now the Y size needs to be 10. Zooming in so I can get everything lined up well. Left click on the active, right click on the active, and slide in so that we've made our contact to either our source or our drain. Do the same thing on the opposite side. And slide it in. So let me guys know when you're caught up to this.
Good.
All righty. So earlier I copied the transistor, but I'm not going to do that now because we're going to be a little bit more efficient in our space utilization here. So I'm dropping another NMOS transistor to the right of my first one. I'm going to rotate it again by pressing Control J. Press Control I to change the parameters to make it 10 by 2. Let's see, I need to set my spice level or set my spice model. Why is that? Okay, vintage up there. Control left click to get my text. Change this to NMOS. Press apply. Make it 1.5 and a 90-degree offset as well, just so the text is the same size and the same orientation. And now I'm going to take this guy, left click on it to select it, and then right click over to this active region and then slide this transistor over. And so what I've done here is effectively this middle contact is going to be my shared source between those two transistors. So instead of having them spread out like I did in the first example, which I'll just pop over to that one real quick so we can see it, takes up a good amount of physical space on the chip. This is a way for me to implement that same structure with those two transistors with their sources tied together in a much smaller package. I'm going to go ahead and put my inactive region over here. Get that guy going. Tie things together. And just so that I'm 100% sure of what's going on, I'm just going to put some annotation text on my drawing here. So it's not going to process this as slice text or anything. It's just literally a reminder to help me remember what's what. So I'm just going to call this the drain of transistor 1. Throw another bit of annotation text over here, letting me know that this guy is the drain of transistor 2. And then I could put some annotation text in the middle here, letting me know that this is the source of transistors 1 and 2. So that's not going to affect or hurt anything. It's just a way for me to keep up with stuff. So let's see. I put my polysilicon to metal 1 layer contact up top. So now I'm going to connect that to both of my gates. Oops, no, let's do it this way. Not giving me any errors or anything. I'm going to run my metal line up from my drain. And connect that over. Run a check. It's not giving me any errors. And now I'm going to play around and see if I can't move this guy closer in so that we're not using so much space. And I'm just going to move it down and down and down until it gives me an error. So that's where I get the error. So that was too far. Was it though? Yeah. All right. So that's as close as I can get that contact to the transistor without it yelling at me. Let's go ahead and take care of our body connection. So I'm going to have a P well contact, put it down here at the bottom, and I'm just going to have one large body connection for both of these transistors. Again, the body connection is really not so much tied to it as it is biasing the substrate to a particular value. I could really make a whole ring around this transistor, and that would actually probably be better, but that'll take too much time. So let's make the X size, let's see. So this 20. No, let's call it 25. You're gonna get it. Overlapping. Press F5, no errors. Tie our source to our body. So now both of the transistors have this one large body connection. Oops. And then lastly, again, I'm going to make my little stub down here and export this as G and D. And the export shortcut is Control E. Now I need to get my PMOS transistor going. I'm going to rotate it. I'm going to change its size. So I believe the math says that we got a 10 by 60. So I'm going to press apply. So I have my 10 by 60 there. I'm going to put a P active contact around here. Make it have a Y size of 10. And I'm going to tie it to the drain. So the drain of my PMOS should be tied to the drain of my NMOS. And I'm just moving this down. To minimize space. So let's press F5. F5 found 2 errors. Let's see what those errors are. Oh, so my active regions are too close to each other and aren't connected. So that's not a big deal, because we'll fix that in a moment. Still getting 2 errors. So now it's saying that my polysilicon for my gate for that PMOS transistor is too close to the other polysilicon, and we fix that by tying them together, because the gate of my PMOS should be tied to the gate of transistor M1 and NMOS transistor M1 and M2. Still getting 2 errors. Let's see. Not liking something. Maybe it's too close to the metal. Let's back this guy off half and half. All right, so that got rid of it. The last thing we need here, or not the last thing, but the next thing we need is our P active for the source contact. So let's make that size. Scooch it in. No errors. And lastly, we need a body connection and well connection for our PMOS transistor. And we can make it in the X size. Let's do 50. No, 60, because this is a 60. And how close can I get? So that's a lot of errors. So let's back it away. That's no errors. So that seems reasonable. And I'm going to export this pin in this top corner to be BDD. So Control E, BDD, and press OK. I need to export BDS2 again. And I'm going to be lazy and just steal my spice text from my first one. Ideally, these guys are representing the exact same circuit. It's just that we've changed the way we're connecting our 2 NMOS transistors a little bit to be more space efficient. And we have put in this PMOS transistor, which is going to be physically significantly smaller than a NWell or high-res poly 2 resistor. So let's check for errors, check for well errors, none and none. So now we'll run simulation. Oh, we can't run the simulation yet. Come on. Sorry, just a second. My laptop battery is saying it's about to die. Because we never set the spice model for our PMOS. So if we go to tools, set spice model, PMOS. Now we can simulate it. Let me share LT Spice. Let's see. So if we look at the drain current of our PMOS transistor and the drain, nope, not auto range, the drain current of our NMOS transistor, 1 ID, that's 1. We're seeing that we're not getting 20 microamps as expected. We're only getting 15. So the size of our PMOS transistor isn't quite right. So our calculations gave us an approximation of what's going on, but we're going to need to play with this a little bit. Unfortunately, I'm out of time because I got to go to that meeting in 7 minutes. So you guys can use the rest of the time to just change the size of that PMOS resistor until you can simulate it and get a drain current of 20 microamps. But before I pop off of here, let's think about this real quick. Do you think your PMOS transistor is going to need to be physically larger or smaller? Anybody have any ideas? Anybody still paying attention?
This is stab in the dark, I guess larger, I'm not sure.
So it's going to need to be smaller. And the reason is that effectively that big, huge chunk of polysilicon that we have there is resistive. And so if we're limiting, if our current is smaller than we want it to be, then we need to take some resistance out.
Makes sense.
Yeah, so try with, like I would say right now it's a, 10 width by 60 length, try 10 width by 50 length. If that gets you closer, they're headed the right direction, and then just keep really making it a little bit smaller until you get somewhere around 20, and then you're good to go. Alrighty, well, hopefully this was, I don't know, less boring than usual, writing crap down and doing math lectures. So I'll see you guys next Tuesday, where we'll do some time deriving how a cascode current mirror works, and then maybe implement that cascode current mirror in LT Spice as well, and simulate it to make sure it's behaving the way we want to. So I'll catch you guys next Tuesday.
Have a good weekend.
You too.